In this video, I'll talk about how to model or calculate the thermodynamic properties for real solutions. And what I mean by that, if you look at what we did last time, I derived this, and I'm going to use the notation of Sandler. So the theta is any thermodynamic property. So theta excess being equal to theta of the real solution minus theta of the ideal solution. And make a note that theta is any thermo property. So that can be HU, volume, etc. All right, so talked about last time, the ideal property is the sum of the weight fractions of the individual properties. That's what you would expect. But we haven't talked about to this point how we would calculate what the actual, this is the real thermodynamic property. And while in theory you could measure this, you could measure what the thermodynamic property is. Again, we want to be able to accurately model this mathematically. So what I'm going to do is I'm going to show you the equations that you would use first. I'm going to mix up the order. I'm going to show you the equations, and then I'm going to do a practice problem. And then when we come back next video, next week, I'll talk about the derivations of those. So take a leap of faith with me, take the equations just as givens for today, and we'll come back and talk about where the equations come from next time. Okay, so for the ideal case, if I wanted to look at the thermodynamic property for an ideal binary mixture, it is the sum of the weight of the mole fraction times that thermodynamic property. So it is equal to, for two components, x1 times theta 1 plus x2 times theta 2. Right, and this is the weighted average, not in quotes, that's actually what it is, weighted average of the property, weighted by the mole fraction. Okay, so what I'm going to try to do mathematically in a model is say that the real property, so no subscript for real, just keep in mind that this is a real molar property, is equal to x1, and I'm going to define something different. So the property over bar 1 plus x2 over bar 2. And the definition of theta over bar is the partial molar property. I know this is new stuff. Again, try and just take a leap of faith with me for a second. But it's defined in a way such that you can clearly see the parallels between the two equations. So the over bar is the partial molar property. That is directly analogous to just the regular old molar property. Okay, so a mathematical definition of the partial molar property is as follows. You can say that the partial molar property of species I is equal to the partial derivative of the change in the property divided by, with respect to the total number of moles at constant temperature, pressure, and number of moles of species I that is not equal to, wait, sorry, I got a lot of emails in a short amount of time and I was getting distracted. So J not equal to 1 is being constant. All right, so what this says in words is, if I add a small amount of one component, okay, mathematically you say that is my change in number of moles. So if I add a small amount of one component, what will be the resulting change of that thermodynamic property? What is the change in the amount, or what is the change in the thermodynamic property of interest? And the caveat here is that temperature, pressure, and the amount of all other components that is not equal to, this should be an I there, J not equal to I. So keep in mind, of course, that the number of moles, the total number of moles, times the molar thermodynamic property is simply equal to the extensive version. So remember the definitions. This is an intensive variable, and this is an extensive variable. Intensive not depending on size, extensive is depending on size. Trying to contextualize to not get lost in the notation and the mathematics as much as possible. Very easy to do at this point. I'm going to try and help that as much as possible. Okay, so this is the definition of the partial molar property. How would one actually use it? And this is where I'm going to skip a lot of the derivations for now, and we'll come back to this, as I said, I promise, next time. But through a derivation, you can show that the theta over bar 1 would be equal to the molar property, theta under bar, plus x2 d theta under bar dx1. And vice versa, you could say that the partial molar property for component 2 is equal to theta under bar minus x1 d theta under bar dx1. All right, so again, skipping the derivation for now, we will circle back to it. I want to start with an example problem such that it's contextualized for you. So skipping derivations for now. All right, so let's try a practice problem. Let's suppose that you have experimental data for the molar enthalpy of a binary mixture at fixed temperature and pressure, and say that this was the data fit that gave you an accurate representation. So you might think, well, if I have temperature and pressure, then why is my molar enthalpy not fixed, right? And every other example that we've done, we've had a Gibbs phase rule equaling 2. So just to show you that Gibbs is changed now, Gibbs phase rule says I have 2 plus the number of components minus the number of phases. So I've got 2 plus 2 components now, and minus 1 phase is equal to 3 degrees of freedom. So if I only have temperature and pressure fixed, that's 2 degrees of freedom, and my last degree of freedom is the composition. So typically the variables that I have a function of is Tp and x of species 1. And remember that x of species 2 is simply equal to 1 minus x of species 1, so we don't have to include it. All right, so how do we figure out what the partial molar properties are? The question is, I'll write it out. Question is, what are the partial molar properties of the two components when the composition is 30 mole% of the first component, 70 mole% of the second component? So I'm going to apply my definition of the partial molar properties here. So first, I'm going to say that the partial molar enthalpy of species 1 at whatever temperature and pressure that I have at Tp and 0.30 is equal to the molar property, so H, and that is given by this expression here. So I just have to plug in 0.3 for x1 in my expression for H, and plus x2. So x2 is 1 minus 0.30 times the derivative dh dx1. dh, oops, partial derivative, right? No, total derivative. dh dx1. All right, and similarly, partial molar property for component 2 at same Tp and x1. So even though it's partial molar property of component 2, it's still a function of component 1. So I should also put in parentheses at Tp and x1 there. So it's h tp x1 plus, or sorry, minus 1 minus 0.30. No, it is minus 0.30. It's not 1 minus because it's x1, not x2. dh dx1. I have that right? Yes. All right, so now all I have to do is figure out what the derivative of h as a function of x1 is. So I'll take the derivative, maybe in a different color, in gold. dh dx1. First term is a constant, so it goes away when I take the derivative. Second term is multiplied by x1, so 45/16. And the third term, I take the 2 out to the front, so minus 2 times 32/15 times x1. That is the derivative. So let's calculate now. Calculate h1. Partial molar h1 is h underbar, so minus 3399 plus 45/16 times 0.30 minus 32/15 times 0.30 squared. So that was h underbar plus 0.70 times the derivative. 45/16 minus 2 times 32/15 times 0.3. Right, an analogous expression for H2. I'm going to flip over to Excel now, and I'm going to show you the calculations there. I'll be sure to remember to screen share this time. All right, so I'm over in Excel, and right before I started the recording, I made a column for X1. This should be X1. I'm going to change that. X1. And I only need X1. I don't need X2 as well. All right, and the next column, I'm going to make a column for h underbar. This is the molar property. And remember, the problem gave me an expression for that. So it's minus 3399 plus 45/16 times x1 minus 3215 times x2 square. All right, and I will copy that formula all the way down. Hopefully. It's on my tablet, so maybe it won't work. It's got to work. Okay, got it. I need to use my pen as the mouse. So I just copied this formula all the way down, and this gives me my actual answer for h underbar. Now I can calculate my h overbar, my partial molar property, at any composition that I want. And to answer the problem specifically, I'll be looking at when x1 is equal to 0.3. So to make my calculation easier, I'm going to make a column for derivative. So dh underbar dx1. This is tricky on my tablet. Okay, and I have an expression for that, equals 4516 minus 3215 times 2 times x1. Found a typo. What's the typo? Oh, parentheses. Yeah, don't need parentheses. Okay, perfect. So now I'm going to have another column. This is going to be h overbar 1 and h overbar 2. Going to apply the formulas that I have for these two things. So h overbar 1 is the molar property plus, it's x2, so it's 1 minus x1, and that is multiplied by the derivative. (1117) Those are the same units, by the way. So it's, did I put the units? Problem doesn't give me units. I'm just going to assume it's joules per mole. Yeah, units are joules per mole. Forgot to write that, but that should have been involved in the problem as well. H over bar 2, according to our definition, is equals the molar property minus x1 times the derivative. I'm going to copy that one all the way down. So highlighting what the answer is, these are our partial molar properties for the composition of interest. Now, bringing it back to why this is useful again. Well, say I didn't have an expression for H underbar. Well, I would have to have an expression for H underbar because then it would be recursive. But I'm going to show you how, from the information of what the partial molar properties are, I could calculate back exactly what this H underbar is. So the molar property now is, remember the definition of it was equal to the weighted fraction of the molar properties. So it's x1 times h1 plus 1 minus x1 times a partial molar 2. And if I copy that all the way down, should notice that the two columns are now exactly matching each other. So if I highlight this column and I compare it to this column, I've gotten back what my molar enthalpy is. So again, the overall goal of this is I'm trying to make a mathematical model such that I can calculate what the thermodynamic property of interest is for a mixture at any composition. So I know this video was probably very confusing. I'm going to stop it here and I'm going to pick up again on Monday with the derivation.